Hi everybody, and welcome to another video looking at some chemical concepts. Now today we're going to start looking at spectroscopy, and before I start getting into a discussion of what is spectroscopy, what do we use it for, and why is it really important, I just want to acknowledge the chemistry teacher who produced this PowerPoint that I'm using in these videos, and that is Duncan Smith from St Paul's Collegiate, who produced this video in 2013. I suspect right now this PowerPoint is being used in chemistry classes all over the country. It is fantastic. Thank you so much, Duncan. Anyhow, spectroscopy. Spectroscopy ultimately is the solution to a chemist's conundrum. What I mean by that is when you do some chemistry, whether you're analyzing something or making something, it's very, very difficult to know whether the thing that you are interested in is actually the thing that you have produced and that is in front of you. Because one colourless liquid looks like another colourless liquid, as you will all know, and it is really, really hard to identify what's what. And that is ultimately the purpose of spectroscopy. It is a study of how light, which is electromagnetic radiation, and matter interact. So electromagnetic radiation, which is a whole range of radiation, ranging from radio waves at one end of the spectrum through to gamma rays at the other end of the spectrum, is effectively a form of energy where energy travels in both waves and quanta. And if you're taking physics, you'll understand a little bit about the particle nature of light, and I don't want to get into that in any great detail. However, electromagnetic radiation comes in a wide range of forms, and it is ultimately a form of energy. Now, what is really interesting is if you take a chemical molecule and you hit it with some of this electromagnetic energy, interesting things can happen. And depending on the frequency of that electromagnetic radiation, you can get different things happening. And ultimately that comes down to spectroscopy. Now, spectroscopy comes in, well, no, spectroscopy doesn't come in two forms, but we use it in two different ways: qualitative and quantitative. Quantitative is about determining how much of something we've got, and we're not going to deal with that in this topic. What we're looking at is qualitative chemistry. That is, what substance is actually present, and how can we use the substance's interaction with light to determine that. Now that still sounds complicated, and I would like to just stress right now that none of this that I'm going to cover in today's video is examinable. This is all background information. Okay, so when we have particles, compounds, elements, molecules, if we bombard them with electromagnetic radiation, if that radiation is at the correct frequency, then some of that energy may be absorbed. But that will depend on the type of radiation, which then determines how much energy will be absorbed. When that energy is absorbed, it can cause an electron or a molecule to go from a low energy state to a high energy state. So we've given it energy. It's kind of like you drinking a V, and all of a sudden you go from your regular low energy state to some sort of higher excited energy state, and you'll bounce around in that high energy state until the energy runs out, and then you'll fall back down to your low energy state again. In terms of molecules, what that can mean is that molecules may start rotating faster or in different directions. They may start vibrating, or the electrons themselves may jump up from lower energy orbitals to higher energy orbitals, and we'll talk about that in a later topic. So, for example, if we take radio waves, which are relatively low energy waves, and we shoot that at molecules, it can change the magnetic orientation of the nuclei in those molecules. Now, various molecules can, or atoms within molecules more precisely, will spin in a particular direction. When you hit them with radio waves of exactly the right energy, they will change their spin and they'll start spinning in the reverse direction. And we can pick that up through a technique called nuclear magnetic resonance. If we use infrared radiation or microwaves, then again, at the right frequency, certain bonds will start vibrating, stretching, bending, etc. And we can detect that using a technique called infrared spectroscopy. There are many other techniques, UV or visible light spectroscopy, atomic absorption spectroscopy, atomic emission spectroscopy, and many others that we are not going to assess in this particular topic. We are, however, going to look at mass spectrometry, which is technically not a kind of spectroscopy. It still has the spectro in the name because we still create a spectrum, but it doesn't involve light. What we do with this particular technique is that we basically bombard the molecule with high energy charged particles, smash it into little tiny pieces, and then identify the masses of those little tiny pieces. That's why it's called a mass spectrum, because it's looking at the masses of all the particles that are formed when we smash a molecule to pieces. We'll look at that later. Mass spectrometry is probably the most complicated of the three techniques in terms of its interpretation. That's why I'm going to leave it till last. Okay, so when we talk about spectroscopy, ultimately what we're talking about is spectra. What is a spectrum? A spectrum is effectively a kind of graph. Any given technique that we use will give us some pieces of information. No single technique is going to tell us everything we need to know. So ultimately, the use of spectroscopy for identifying the structure of organic molecules, which is what we're going to do, is a matter of, it's a bit like a jigsaw puzzle, really. We're taking little pieces of information from here and there and the other place, and we're putting them all together to determine the structure of a molecule. So, for example, we could have nuclear magnetic resonance spectroscopy, where we take our radio waves and we shine them at a molecule. The nucleus of that molecule can act a bit like a magnet, or the nucleus of the atom, I should say, acts a bit like a magnet. And if we hit it with just the right energy, then it can cause that magnetic orientation to flip. Now, that's all very technical, and luckily you don't need to know any of that. But what's really cool is it can tell us how many unique carbon environments there are in a molecule, and I'm going to get onto that later, and what things are bonded to those unique carbon atoms. And we get spectra that look something like this. Now, this might not look like a spectra. This might just look like a bunch of lines, but each one is actually a Gaussian-shaped curve. It's just very, very narrow. I'm going to talk a lot more about these spectra as we get into it, but that's what we talk about when we talk about an NMR spectra. Now, I should say there are many types of NMR spectra, and we're only going to look at carbon-13 NMR, so we're only looking at the carbon atoms. With infrared spectroscopy, we have the bonds that exist within different molecules, and if we hit them with the right frequencies of infrared light, then some of that energy can be absorbed as the bonds rotate, vibrate, stretch, bend, and all that kind of stuff. And so from infrared spectroscopy, we can learn about the functional groups that are present in a molecule, and our spectra look something like this. That's a really ugly looking spectra, and what this is looking at is how much infrared light is transmitted through the molecule and at what frequencies is it absorbed. But I'll spend a lot more time on that later. The final type of spectra that we're going to look at is mass spectroscopy. And as I said before, we can take our molecule, bombard it with high-frequency charged particles, be they electrons or positively charged ions, and that can effectively smash the molecule into pieces. The different pieces will then be recorded in terms of their mass, and so we can identify what the molar mass of that compound was initially, and we can identify the types of groups present within the structure and how they're connected to each other. So ultimately we can determine a lot about the structure of a compound from mass spectrometry. And the mass spectra looks something like this. And as I said, these are the most complicated type of spectra to interpret. So we're going to start at the beginning first, and we will finish off with mass spectra at the end. I will see you in another video when we start talking about some of the basic ideas associated with spectroscopy.